fell, the figures fell below the threshold. So that was the reason the
So
paper
it means
provided.
that they were able to determine that they are using reflective, and then now they realized that the indicator loadings were far below, so they had to
Yeah,
delete it, right?
yeah, yeah.
Mhm. So they deleted them, and then probably it was left with three. The point is that
Yeah.
sometimes you can have negative loadings, and normally it
Okay.
occurs when you have you have when you are setting the questions, you reverse coded some of the questions. So in that case, if you are doing the data cleaning, you're supposed to um, do reverse coding so that it will, change. It will change the values and then it will be on the same path. Uh-huh. So in that case, you don't have that negative value.
Okay.
So we have learned that the threshold is 0.7. So if you have, let's say, 2, it means that you are supposed to take that one away. But there are a few exceptions. For example, if you have, so let's go to the model here. So this is our model, right? So this is what we have been doing so far. So let's see something here if we can demonstrate what you asked. So you see this one, we
Yeah.
have all of them to meet the criteria. So let me see. I think I have other models. Let me see if I can run some of them in different workspace. So, mm, so okay. So let's say let me see if I can get some example here. So let me run this one and see what happens. Okay, so here the color is white and black because I changed it. So you can also change it. I think we have done this before. So there's nothing new that we have done. We realize that when you put this one, this one, the AV is 0.49. It does not meet the criteria for average variance extracted. So what can we do? What we can do is that we have to take away one of these, okay, because the reliability has been met, the alpha has been met, the rho C has also been met, but the AV has still not been met. So you have to take away the least one.
Okay.
And if you take the least one, it has to improve the model. So if you look at these B1 to B6, what do we have? We have B3 here. So you can take away this one, right click and then delete. And then you just activate this one to automatically run it for you. So let's see what happens. Now the AV has been met. We have 0.45, 0.545.
5-4.
So,
Yeah.
so if you have data like that and then the criteria are not met, that is one way to go about it. You have to take them away. But whenever you do that, you're supposed to run it and see, because once you take away any indicator, you have to run and see what it does to the model. So let me undo and let's see what happens. Before we deleted the B3, we have R squared to be 0.370.
Yeah.
Now let me redo. Once I did that, now the R squared is now 0.366, and our AV has improved. So this way is better because now this has met the criteria. Is that right?
Yes, please.
Yet we still have B6, which is not up to 0.7 or more than that. So what do you do? You're supposed to delete or you can maintain that. So now let's see what happens when we delete B6. So we have here to be 0.36, and although everything has been met, but let's see what happens. Does it improve the model or does not improve it? So let's delete this one. Good. Now what has happened? when we deleted it, it has improved the model. Before that, it was 0.3. Where is it? Let me undo again. It was 0.366. Now, after deleting, it is now 0.368. So it has improved the model. Is that correct?
Yeah.
So in that case, you can leave it this way and then report on that.
But please let
But
me see it AVA. But let me see it AVA. Put it on it. Let's see the it AVA value. Okay.
Yeah.
the more you
That's
delete,
what's
the,
about.
the higher it goes up because it takes the
Okay.
average. So if you have lesser figures or lesser values, it reduces the average variance extracted. So the more you have higher values, so it's like the average of these ones, 0.8, 0.7, 0.68. So if you delete the lesser values, that's where we get to. But look at what has happened. Can you see that the reliability has come to 0.69?
Yeah.
So let's undo and let's see what also happened. So I think this way is better.
Okay.
Because now we have met our criteria for all of this. So we can maintain this one and we can justify,
Okay.
right? But whenever you want to do some deletion, you are supposed to also consider the other latent construct or variables. So you don't have to just be on one side of the construct and be deleting. No, you just have to, because once you take away one of these, it also affects the others.
Okay.
So let's see. Uh, Before we deleted this B6, let's see what happens here. You see, U1 has 0.789. Now let's delete it and see what happens to the U1. Now it has come to 0.688. So whatever you do to one indicator, it also affects the other indicators as well.
Okay.
That is why the house price has also been affected. Okay, so we don't deal on one side of it and then deleting, trying to make sure that it meets the criteria. You can start somewhere and then you come to the others and see what it does to the model. So that is the deletion. So maybe the paper that you saw, it was the case because they didn't have much indicators or questions for the respondent to answer the questions. That is why it's always advisable for you to set more relevant questions that are valid, such that when you are doing the deletion, okay, you have enough indicators to help you do or build better model. I don't know if your question is answered.
Yes,
But
please.
I don't think you can leave it as 2 and then you leave it as that. You can leave it as 2 if you are dealing with formative. Okay, so formative, we discussed that formatives, normally the indicators are not really correlated to each other. So in that case, this is a standalone variable. This can be an income variable. This can be maybe education. This can be another whole indicator on its own. So in that case, it can be even one, because if you are dealing with maybe secondary data from reputable sources like Red Bank or WDI, WGI, Red Government Indicator, any variable or any indicator that you download, it is on its own. So it will be on its own as this. So it can even be one. That is all. I don't know if your question is answered.
Yes, please. Thank you very much,
Okay.
sir.
So let's look at this one. This one has been met. This has been met. This one has been met. This one has also been met. Okay, so that is it. So this was the model that we created the last time. Today I want us to look at PLS predicts or CV parts. Okay, so when you go to calculate, you see that you have this PLS predicts. Okay, so let me show my slides. So PLS Predict is an algorithm that was developed by Shmuley et al. 2016 to assess the predictive power of PLS path model. And this technique employs k-fold cross-validation. So k here is a variable. It's a variable that represents a specific value. Okay. And it divides the data into training and then holdout sample to generate and evaluate predictions. So those of us who have done machine learning before, you see machine learning, you have the testing data and you have the training data. Okay, so you group your data into two groups. That is the testing and then the training. So here, the testing is the holdout sample data. And then the training data is the data that you're going to train on, and you're going to use it to predict the holdout sample. So this method serves as a diagnostic tool to detect potential overfitting of the PLS model to the sample data. And it provides out-of-sample prediction metric that complements traditional in-sample model fit assessment. So here there are two key parameters that we look out for: the number of folds, okay, and then the number of repetitions or iterations. So let's look at that into details. If you go to the software, default number of fold or segments or groupings are normally 10. Okay, so in k-fold cross validation, the complete data set is partitioned into k equals I. So a specific number of, so normally if it is 10, then it divides it into 10 different equal size or folds or segments. So the software iteratively uses k minus 1 fold for the training the model, while the remaining fold serves as the holdout sample. So if the default is 10, it means that it's going to group your sample data into 10 minus 1 fold. That means 9 fold or 9 segments. So assuming that your total sample size is 350, it's going to divide it into 35 groups of 10. So each segment or fold is going to have 35 sample in it. All right. And out of these 35 samples for that group of 10, 9 of these groups are going to be used for the training. And then 1 is going to be used for the holdout or for the testing phase to see how best or how well our model predicts the out of sample data. So the model is then estimated 10 times. That is the iterative process. So once it groups it, it iteratively runs on it 10 different times. Each time using 9 fold. Okay, so anytime it uses the total of 315, that is the training stage for the training, and then 1 fold, that is the 35 for the prediction. Okay, so that is how the fold works. And the software does it for you, so you don't have to be worried about it. And this is the repetition. So repetition specify how many times the entire specific key fold cross-validation process is executed with different random data partitions. Okay, so since the data is randomly allocated to folds, different runs may produce varying prediction performance metrics such as the root mean standard error, the mean absolute error, and then the chi-square predicts. So running multiple repetition provides more stable and reliable average prediction error estimate across different data splits. Okay, so that's the iteration process. High repetition increases computational time, but it helps to improve robustness of the predictive accuracy assessment. So with this, the software does these repetitions, and then within seconds, you're going to have it. So this is just a sample image or depiction of how it works. So if you have 4 fold, then let's look at this data sample. We have it that's grouping them into 666 different sample data. So it picks just one of the group as the test, and then the remaining will be used for the training, and then the training will be used for the testing. All right, so it does that iteratively for so many times. So here, the first process will take place for the first 6, and then the second repetition will move on to the next different random samples. It does that repeatedly until you get your results. So we can just run that, and then we see how. So using this same model, this is what we did the last time. So we can delete this one. This was gender moderation, right? So we can delete this one for now. And then this is also skill development moderating. You can, if it is part of a model, you can delete that. But we just want more space to work. So what do? You go to anytime you start the SEM, you have to just run the PLS-SEM to know how it runs. First, check your measurement models and then the structural models, which we have done before, and we realize that everything has been met so far. So now today we are looking at the PLS predicts, okay, and then just as we mentioned earlier, by default it groups it into 10, and then the repetitions are also 10, and then we can leave these ones on default. You don't have to change anything. This is standardized, and then you see we have when we did the moderation last week, or I don't know, last week or last 2 weeks, we grouped some data. So anytime you want to run something, you come to data, you see that all the groups that you have done. So we grouped data, the gender into males and female. And I remember we also grouped this. This is the number of experience or number of years they've been in business, if you can recall that. So that is it. So you just have to come to PLS predicts and then start calculation. So it is going to run automatically for you. Good. And then we can come to open report. So with the PLS predict on the graph, you don't see anything here, but you can come to the final results. Now we made mention of Q square, right? So normally your Q square should be greater than 0. Or once you are, even if you are new to PLS, we realize that you should have green. Once you have green, it means that you are good to go. So you can see that our Q square predicts. That is used to assess the predictive power of our model. Okay, so this is the PLS predict manifest variable. So the MV is the manifest variable summary. So the manifest variable is the same as the indicator. As we have learned earlier, we said that the manifest variable is the same as the indicator load. So here our AO1, and these ones are for the predictive model or the latent variable which is being predicted. So we have here the behavioral engagement and then academic outcomes. And these ones are the ones we want to test to see whether they have predictive power or not. So we come to predictive power and then run again. And then run again. You come to open full report. So PLS predicts manifest variable summary. So the overview is what we see here. So our Q-square predicts, which is used to assess the predictive power, is greater than 0 for all the manifest variable. And that's why it is green. So it means that it is being predicted well, or the predictive accuracy is well established. And then if you don't want the manifest variable, you can also check for the latent variable. So this one gives you the report on the latent variable score. So overall, the behavioral engagement is being predicted, and it is approximately 0.5. Okay, so it is more than 0. So this is good, on a good note. And then academic outcomes also more than 0, which is also on a good note. So approximately 50% is being well predicted. All right. So we are good to go. We also have, we can also report on the PLS-SEM root mean standard error. We have the mean absolute error. And then the LM is the linear model. So we can compare the score of our linear model and then that of the PLS-SEM. Okay. And that will also help us to establish the fact that is using the PLS-SEM a better fit compared to the normal linear model that we know. Okay, so you can do that by copying this. You can just compare these values. Okay, so as you can see that these ones are in green, it means that the errors predicted by the PLS-SEM is giving us lesser values compared to that of if we use linear model. Okay, so you can see from here that this is 0.5 compared to this. It means that the error generated by the linear model is higher than that of the PLS-SEM. So it means that the PLS-SEM is a better fit. Okay, so we can just copy that into Excel. And then so just copy that. And what we are looking for, what we are comparing now is that the PLS-SEM model and then the linear model. So we can take away these ones. And then we can check the difference. So you want to see that this is equal to this particular one minus the score for linear model for the RMLC. So that of this equal to. So you can just double click this one, or you can scroll, you can drag and throw here. So you can see that we have negative values. It means that the linear model RMLC is giving higher error compared to that of the PLS-SEM root mean standard error. That is why we have negative values here. So it means that the PLS-SEM is a better fit, or it is good that we use the PLS-SEM. We can also do the same for the mean absolute error. So you can calculate the difference and equal to this one minus out of this. So you can see that we have here to be negative, negative, and here is positive. So it means that the error predicted by this particular indicator BE3, okay, comparing this one to that, the error predicted by PLS-SEM is much higher than that of the linear model. Okay, so overall, we have much of these values giving us negative values, which establishes the fact that the PLS-SEM is a better fit. Okay, but ideally, what we report on is the Q square. So once we have these to be greater than 0, we are good to go. You can also add these ones as well for better transparency. Okay, so that is it for the PLS predicts. You can better also present on these ones. Okay, so you can present on these ones. So if you are presenting on this one, the latent variable, there's no clear cut rule. Okay, the whole idea is that we want to reduce error. So the lesser the better. So if you have 0.6, you have 0.6. It means that this is even better than having less 0.8. So you can just predict on these ones and then as of now, there's no clear cut rule to, I mean, or for us to determine the cutoff point for determining RMAC and then MAE. Okay, so that is it for the PLS predicts. I don't know if there's any question on that. Is there any question?
For me, I didn't get anything.
Yeah, really? Which part?
When you started calculating the PSLM credit,
The predict.
yes.
So in summary, what you are saying is that, okay, you want to know whether your dependent variables are being predicted well with accuracy. And then in PLS-SEM, what we use to do this is the PLS predict. Just select that, leave everything by default, and then start calculating. And what you are looking for is that your KO square should be greater than 0. So you just come to reports and then come to PLS predicts. And this is the manifest variable, the indicator variable. You can see that the KO square predicts is greater than 0. So this is what we are looking for. Once they are greater than 0, it means that it gives us a better predictive accuracy. And then you can go to the latent summary. And the latent summary gives us the overall summary for each of the latent variable. And we can see from here that the Q squares are greater than 0. So it means that we have better predictive accuracy. So that is all for the PLS predicts. In summary, if you are to summarize that, that is all you are looking for. Is that right? I don't know if you get it now.
Yeah, so once the Q square predict is greater than 0, that means the latent variable, the independent variables are actually predicting
Yes,
the
the
constant.
predictive accuracy is good. That is all.
Okay. Okay.
That is all. That is all. So that's what we need. That's what we need to predict. That is all we need to. Sorry, to report on. Okay, so you can also find the histograms and all of that. I've not really seen any paper reporting on this. So you can be the first to report on that. Okay. Hmm. So this one will help us to know whether the data is normally distributed or not. The data set or the construct are normally distributed or not. So this is the density. And then the image here we see here is the normal distribution curve. Right. So that is it. Any other question? Okay, so then we can move on to quadratic term. Quadratic term. So in Smart PLS, ideally, basically, whenever we are running models, we always assume that there is the relation between the various constructs are linear. All right. The relation between the dependent and the independent variable are always linear. But it can also be the case that the relation between the independent and the dependent variable is not actually linear, but maybe some kind of non-linear relationship exists between them. The software also gives us this opportunity to also assess linearity and non-linearity. Okay. So far we have learned linear relationships where we assume that the relationship between the exogenous construct, which is the dependent variable or dependent latent variable, and then that of the dependent, which is the endogenous construct, is linear. So in that case, if it's linear, our y is equal to the estimate, and then the b1 is the coefficient, and then the particular variable of x plus the error term. So it means that a y-unit increase in x always produces the same change in y. That means there is a constant, okay? And then the relationship can be represented as a straight line in the scatter plot. And then the path coefficient, which is the beta estimate, the B1 we see here, captures the constant rate of change. Okay, so with linear relationship, we have a constant beta, and that beta is used to capture the rate of change at any point in time. So the real problem with assuming linearity is that in real world cases, for example, let's consider this question: does increasing employee training always improve performance at the same rates? So at any point in time, if we are increasing employee training, if you are to always train our employees, is it always the case that it's going to improve the performance at the same rate? So this is something that we are supposed to think about. So it is possible that at the lower level, when you begin to start to give them the training greatly will improve performance. Okay. So at the beginning of the training, because they don't have much knowledge about what they are supposed to do. And for that reason, you want to give them the training. When you begin, it means that the training is going to greatly improve their performance because at that point, they are now learning. They are now learning. And it will get to a point, the training that you give them is still the same, or maybe always increasing it, but the performance that they are going to put out is not going to, always increase because already it could be that what you are training them is maybe repeated, or maybe probably even if you increase it, they already have much knowledge about that. And the rate at which it's going to improve performance is not going to be the same as when they started learning. And then at very high levels, additional training may have diminishing returns or even negative effects. So at a point, you can be giving them the training, but the rate at which it's going to improve their performance is not going to really increase. Okay, it can be diminishing. So you're giving them the training, but the rate at which their performance is increasing is actually diminishing. So it happens that case. In that case, this is what we refer to as the nonlinear relationship, or others will call it curvilinear. Okay, so it does happen. So if you don't do that, what is the consequence? The consequence is that it could be that we might be underestimating or we might miss the true effects. So you want to predict how employee training predicts their performance. And then you have built in your beta and all of that. If you use the linear model, it means that you might be underestimating the true effects of how well employee training improves their performance. Also, your conclusion might be incorrect. Okay, so it happens a lot in if you don't take. That's why you're supposed to do this measurement and all of the structural assessments for the purpose of giving out accurate and then true reflection and conclusions about what you are predicting. Okay, and then at some point, you can also be missing the tipping point or the optimal level. So curvilinear helps us to know at what point, what is the maximum or the minimum level that we can reach, such that if you go further, we are going to have diminishing returns. Okay, so the nonlinear relationship helps us to unveil these points. Okay, so now what is quadratic effect? The quadratic effect captures the curvilinear or the nonlinear relationships between two constructs where the effect of x on y changes depending on the level of x itself. Okay, so it tells us to capture the nonlinear relationship between x and y depending on the level of x or the dependent variable, depending on the level of the dependent variable, how the level at which our dependent variable is, whether it is at low, moderate, or medium, or it is at its highest level. So we can put it in the equation like y, which is our dependent variable, is equal to b1 x. The x here is the linear one, x to the power 1, okay, plus. So the x captures the linear relationship, and then the b1s are the coefficient, plus the b2 with the x squared term. So the x squared is what captures the quadratic effect. And these are the coefficients of the quadratic effects plus the error term. Okay, so B1 is the linear effect of x and y. B2 is the quadratic effect, and then the x squared is the squared term, the predictor. So it means that what the software does is that it squares the x. Okay, it squares the x. It squares the x. So what is the key insight? The effect of x on y is no longer constant. So here it's going to depend on the level at which our x is. It's going to be dependent. The effect of x on y is going to be dependent on the level at which our x is. So we have different types of quadratic relationships. So look at this image. We have the inverted U shape. So with the inverted U shape, our estimate is always greater than 0 and then less than our B1 is greater than 0, and then our B2 is always less than 0. Okay. So what is our B1? Our B1 is the linear term, and then the B2 captures the nonlinear term or the quadratic effect. So here, inverted U-shape relationship, which is B2 less than 0, means that it is a negative quadratic term. So y increases initially at x. Y increases initially as x increases. So you can see that our value of y will increase once our x is going forward. So we have 0 here. But somebody has posted, what is that? There is something on the chat so you can find out, and then I think there's a form that you're supposed to fill. Okay. So attendance. Okay, that's right. That is right. Oh, thank you for reminding me. So are you doing that for me? The attendance, how are we going to capture that? Let me capture that and then. It means that we have about 8 to 9 people who are, excluding me, so we have about 7 people who are consistent. Good. So I'll share that. Sure, after the class, I will send it to the executives. So as I was saying, as x increases on the x axis, our y will also begin to increase. Okay, if this one is increasing here, you can see that it also affects because it is on this line. So the y will also start to increase initially, and then if x gets to this point, that is where y reaches its maximum. Okay, and then if you go further, it means that anything that happens, you're going to have it to decrease. So for example, work hours and productivity. So productivity rises up to a point, then declines with overwork. So when it begins to start working, just as I am talking right now, when I started talking, the energy level was so high, but at a point you realize that it will start to, I'll get to my maximum limit, and then the rest will be that the energy level will start to diminish. So this is it. That is the invented U shape. And then we have the opposite to be the case. We have the U shape itself. Okay. So with the U shape, our the beta coefficient is always greater than 0. The invented one, our beta coefficient is always less than 0, which is negative. So if you see that, and that gives us a positive quadratic term. So here, y decreases initially. So as and when x goes up, our y will start to diminish. Our y will start to what? Diminish at the point. And then at this point, it will get to its minimum. And then once you go further, it will start to what? Rise. It will start to rise. So risk taking and performance. Too little or too much risk both lead to lower performance. So as and when you take on too much risk, there's a possibility that your performance will what? Diminish. And then at a point, it will start to increase. Let's move on to the third one. The third one is accelerating positive quadratic effect. So here, our B1, which is the linear effect or the linear estimate, is greater than 0. And the B2, which is the quadratic effect, is also greater than 0. The positive effect becomes stronger at high level of x. So that's when x goes up, you realize that the y will also keep on what? Increasing. That is how it is. So the higher the x value, the higher the y value. Okay, so if it curves inward, it means that you can be going further with your x, but your y will start to, it will be increasing though, but it will be increasing at a decreasing rate. So that is how, so this is the accelerating positive or the J shape. Then the last one is decelerating positive ceiling. Okay, so here it is still positive. The positive effect weakens. And so as and when the x goes up, then it also starts to what? Diminish. So our B1 is greater than 0. That is the linear effect. And then the B2 is less than 0. So as and when x goes up, the y becomes negative, right? So that is the decelerating positive effect. So all that we have learned so far, it is very common to how moderation effects operate. But what is the difference between quadratic effect and then moderation? So moderation tests the interaction effects. Okay, whether a third variable m changes the relationship between x and y. Is there any modification? Does the relationship between x and y strengthens or weakens when we introduce m? So that is that is what we term as moderation. And then the quadratic effect test whether x is the value of x own level changes the x and y relationship. Okay, so here it means that we have not introduced any new variable, but we are just hinting on the fact that the dependent variable at different levels of the dependent variable, does it have any influence on its own relationship between x and y, or its own relationship between y? That is all. So this is the equation as we have done that before. So what happens with moderation is that the new variable that you're introducing, which is m, it multiplies the dependent variable, sorry, the independent variable, which is the x, and it creates another construct for you or variable for you. So we can see that here we have y is equal to b1x. So this is the linear term plus the b2, which is the new variable that you have introduced, which is the moderator. And then the moderator multiplies itself by the independent variable, and it creates another term or another variable. and then this is our real term. But the case is different with the quadratic term. With the quadratic, it is the same x value, which is being squared, okay, to form the quadratic effect. So here with moderation, there are two different variables, but with quadratic effect, there is the same variable that is being squared. And the concept behind the two is that with moderation, it looks at the conditional effect, and then quadratic effect looks at the curvilinear or the nonlinear effects or self-moderation. Okay, so in the software, we learned that you just have to map your new variable that you've introduced onto the arrow, the path coefficient. And then with the quadratic, we are going to look at that using the quadratic effect option. Okay, so we can try that here. I think we've already done the moderation before. So this is this is the moderator. We just have to map it on the lines. So all that we see here are all moderators. So with the quadratic term, we have this quadratic effect here. So you just have to move your mouse to quadratic effect. And then once you click on that, you realize that you see this click on it. So now if you want to create a nonlinear relationship between data access and then behavior engagement, you just have to click on it, this one. So once we have the quadratic effect here, just click on that. And okay, I think we were on the PLS-SEM, so let's move away from here. So let me come to PLS-SEM and then calculate. Good. So now make sure that we are always on the PLS-SEM. Now you come to select. So let me delete this moderator so that we can have simple model. We can even delete this one so that we can have very simple model to talk about. So now we have these direct relationships. So we are looking at these three. So now we want to know whether digital access has a non-linear relationship on academic outcomes. So we just have to select the quadratic effect, and then we click on where we see the click. Once you do that, because my software has been automatically activated here, recalculate automatically. That's why we see that it automatically calculates. Okay, so if you click on this, it means that the quadratic effect term has been generated. All right, so I can click on this as well, and then I can also click on that. So it means that we have the digital access, we have the platform quality, we have the learning support. All of these quadratic terms have been generated. So that is what we see here. All right. So let's finish the slides and then we come back to this proper. So when should you test for quadratic effects? When your theory suggests a curvilinear relationship. All right. So for example, too much of a good thing, that is the effect, the diminishes returns optimal levels and then threshold effects. So just like when we eat, the more we eat, when we start to eat, you know, the level at which you desire to eat increases. Okay. But at a point, you realize that your level of satisfaction starts to diminish. You don't want to even take in more. You might be eating, but you don't want to be taking more because you are almost getting full. So if you are hungry, your desire for food is higher. Once you start to eat, your desire or your desire to eat more will start to increase. But at a point, you realize that it starts to diminish. All right. You can also consider using quadratic theorem if previous studies have found nonlinear patterns. So during your literature review, you have realized that most of the literature that you've encountered, they mention that the relationship between what you are looking for in your study at a point have had some nonlinear patterns. In that case, you might want to consider a quadratic effect as part of your model. Okay. And then the linear effect is weak. When the linear effect is weak or not significant, if you realize that the linear effects are mostly weak or not significant, you might want to consider quadratic effect because probably it might be the case that the relationship that we are looking at is not really linear, but it might be non-linear. So you might have to consider the nonlinear effect such that probably you might get significant values. In that case, you might be convinced that yes, what you're looking for is not really linear, or what you want to do is not a linear relationship, but it is more non-linear in nature. Okay. So a non-significant linear path may mask a significant quadratic relationship. And then scatter plot of contrast score show curvature. So you can plot your variables in the form of scatter plots. And if you look at how the data is being clustered, and you see patterns where it is not linear in nature, but it shows or demonstrates some kind of curvature, it means that visually, so through visual inspection, you might review a curved pattern rather than what a straight line. Okay. In that case, you might want to consider quadratic effects. And then if you want to rule out nonlinearity, okay. So as part of your linear model, sometimes you might want to emphasize that yes, it is my um the relationship that you have established in your study, it is actually linear and not non-linear because sometimes for those of us who are in econometrics, you realize that whenever you define a model, it's always advisable to add robustness checks. Okay. You just want to be convinced that it is not out of the blue that you have chosen to use a particular model. It is not out of the blue. Why didn't you consider linear model, but we want to do PLS-SEM? Okay, so the same way in economics, we have so many different models. We have regression, we have Discord-Cray effects, we have system GMM, we have a lot of them. Two-stage linear, we have instrumental variables and the rest. So do you just choose any of them? You just have to you just have to go ahead with our assessment. And based on what we find, that is where we be convinced to okay, go for this particular model. Okay, so now we are with our model, we just have decided to go for the linear, or we are assuming that yes, okay, the relationship between that and this x and y is linear. And for that matter, we want to convince we want to be convinced or we want to rule out the fact that it is non-linear. In that case, you might want to consider assessing the quadratic effect of the relationship such that when you find out that the relationships are not significant, you can indeed say that yes, the linear model is the best fit. All right. So that is, you can do this nonlinear test to rule out nonlinearity. You can also make reference to these materials. I'll send a slides to the group, and then you can make reference to these papers. Has Sasted or whatever, Ringo, and then we have Basco. and then we have Enhance 2016. All of these reference materials are very good. I believe that to enhance your knowledge on how to go about this further, if you want to learn more about this nonlinear relationships. Okay, so now we can now go back to our software. Basically, there are two-stage approaches. First, you have to estimate your main model. Once you are done, you just introduce your quadratic model. So we can look at this, and then you can call it a day. Already, we have established our linear model, but let's take it again. First, run your.
Sir.
Yes, I was.
Yeah, please. So what happens when you don't delete the the moderation?
Oh,
Before
okay.
starting,
So
you
yeah, I think I did that because I wanted enough space. So you can be dealing with
okay.
if your model is if you have a moderation in it, you have to consider that. Okay, so let me see if I can undo that. Let me see. Let me not save it. Let me come up. Good. So this is the original model. I don't know if you can see this from your side.
Yes, please.
Okay, then we can go ahead with it. Okay, because we're having a lot of models, that's why I wanted to delete those ones. So
Okay.
if that's the case, then we can go ahead. Because once we introduce the quadratic, we're going to have so many here. So first, let's run our PLS algorithm. So we have it, and then you have to, now you're expert. You know that you're supposed to assess the measurement model. And once all of these things are met, you are good to go. And we have done that already. So then we want to introduce nonlinear effects. So let's assume that we are doing linear relationship with this, but we want to rule out, because one of the reasons why you might want to consider quadratic term is that you want to rule out the fact that what you have done is linear relationship, or the linear relationship is the best fit. Okay, that's the reason why you might want to consider quadratic. So let's do that. So you just click on the quadratic, you click on that. So let me deactivate this one so that it doesn't run. You click on that, click on that, that. So you realize that all that we have been clicking on is on the direct path. So it is not applicable to this moderation construct or latent variable. Okay, so the quadratic terms talks about the fact that the independent variable squaring itself. So what that we have done so far is that it is the relationship between this and that. So here, this value here is the relationship between this and that. The quadratic term here is for this one, and then for that one. Okay. So this one is for the relationship between platform quality and that, and then this and that. So it means that this particular QE here is the square of PQ, and then that of the square of PQ predicting that, the square of PQ predicting that. So it is for only direct path. So now let me automatically run it again. So now I have run it, and we can see this is the basic path that we can get. And let's see whether it is significant. So we've learned that if you want to get significant values, what do? You go to Bootstrap. Okay, so you can go to Bootstrap and then we start the calculation. So let's wait for it to run. Good. So Let me turn off this measurement to p-values, so that we can have very simple. So now we can see the significant values here. I want to move this one so that you will see. Let me find this one. So that was the reason why I deleted the skills development, because it is a moderator and it's not going to be affected by. But if it is part of a model, you can include that just to ensure transparency. Okay. So now you can
I
see
get
from here.
clumsy now.
Okay, that's good. So if you wanted to look at the quadratic effect of this BA and then that of AO, here's the beta coefficient, because already you have set our structural model to path and then p-values. So once it is set to that, you can see them here. So if you set it to blank, you cannot see them anymore. And don't forget, this is the structure. So anything that relates to the structure, the significant values, you can see them in the structure. Okay, so let's turn that into the coefficient and then the p-values. So you can see that the quadratic term of BE and then AO, the beta coefficient is positive, but it is not significant. Okay, so let's look at this one as well. I don't know if you can see it. If you cannot see it, then let me take away this one
We
from
use
it.
that 3D film.
Please come again.
You come too clumsy. Can we get
Yeah. So let me take away some of them. So let me take away this one. And then you can also hide. You can hide this one. Let's hide them. So now you can have them here this way. Let me bring this one here. And then let me bring this one here. Okay, so now I think this one is better. So let me recalculate. Good. So now you can see them clearly. The relationship between this and that is not significant. And then but you can go to full report and let's go to path coefficient. So now the quadratic terms are here. We have this one. So the quadratic term begins from here. So this is not significant. This is not significant. This is not significant. This is not. This is not. So it looks like the quadratics are not working in here. So this can be a robustness to our study, right? This can serve as a robustness to our study. Just as I mentioned here, we can use this one as what? A robustness check. You can use it to rule out non-linearity. So here we can say that our model is robust to linear. It is robust to linearity or to linear assumptions. All right. So that is it. Any questions so far? Any questions so far? So that is the linearity assumptions, and then the nonlinear or the quadratic effects. That is it. So let me go back to.
So in case you are reporting, hello, sorry. So
Okay,
in
go ahead.
case you are reporting, yeah, so in case you are reporting, now that the quadratic effect is not significant, if you leave it out and just write it in your write-up that when you test the quadratic effect, it was not significant, is it not good to go back or you have to show?
That is when you are using that as robustness. So we can create a separate session as robustness test. Okay. And there are several robustness that we can look out for. So one of the robustness that we can do is the quadratic effect to establish the fact that the relationship between the constructs are linear, not nonlinear. So in that case, you can just report on the quadratic effect alone. So this is the direct effect. So this is direct effect. You can report on only this one separately as robust test. In most of the economics paper, we do robustness tests. So let me see. And recently, I think there was a paper I did on SEM. I did some robustness. So you can just report on this one alone. So this can be the heading robustness test. And here the table is what? I just call it quadratic effect result. Or it depends on you, maybe nonlinear results. Then you have to explain by justifying your choice of linear linear assumption. The reason why you chose linear, that is all. That is all. So I think when you do this, it is also good and it will give you upper hand. The reviewers will know that yes, you know what you are doing and you have justified your choice of your model. That is it. Any questions so far? Any other question? That means we are good. Okay. So I think we can look at one
Professor,
last thing. Yes, sir.
yeah, I tried following, but at where you do the
At where I don't know. Am I the only person who cannot hear you?
No.
my network
Okay.
was down.
Okay, go ahead.
Yeah, yeah, I tried following, but uh, where did you go for this interface to show where the table after?
How did I go for the interface to show? This one. This one. Are you talking about this one? Hmm. I think his network is still not helping him. Oh, I think he's not on the line. So when he comes back, you know what we can do. So let me come back and not save it so that I can go back to where I started from. So we can look at one last thing and then we can call it a day. There is this one as well, important performance map. Okay. So this one, the software will group your data sets into two different aspects as to how the construct perform, and then its importance. Okay, so when you start, you just have to choose one of the dependent variables, and you just start calculating. I don't know if the person was asking a question. Are you back? Okay. So now I was talking about the IPMA, Important Performance Map Analysis. This one will create a map for you. And so what do? You just come to IPMA, and then you just start calculation, open full report. Now, you can see the report here. This is the path coefficient, as we already know. And we can see the performances in here. Okay. So we have the latent variable score performance and then the manifest variable performances. Okay. So we can see from here. Let me report on this one. Okay, so gender is negative because it is possibly because it is the moderator. Okay, but these are the key variables that we are considering. So let me take away the gender from it. So now you can see that from this table, it shows that skills development is performing better. Okay, so the score for the skills development is 58.42 compared to the other ones. Then this one follows. Okay, then behavioral engagement. So it means that digital access is really a problem. Okay, so this can be something that you can discuss in your study. That it could be that most of these students, once we see that it is not performing really well here, it means that there is lack of data access. Okay, so that is something that you can also discuss in your study. You can also see that in the form of manifest variables for each of the indicators. So you can trace back to your study how you answer the questions, and then you can also find that in the discussion of your study. And you can also see that pictorially, all right? You can see that pictorially. So here we have the performance on the left and the importance on the as your X. So now for each of the colors, the behavioral engagement is this one. And then on the X-axis, we have the total effect. So you can see the total effect in here. So let me go for the list and then let me copy. So you see the moderations are also showing here. But let's look at the effects. Okay. So I can create a column here. So behavior engagement and then academic outcomes. Okay, let me show you that here. So let's look at the effects. Behavior engagement and then academic outcomes. The total effect is about 39%. And then that of digital access and academic outcomes, we have about 34%. Okay. We have gender. Gender is a moderator. And what else? Learning support is 0.189. So I wanted to put them together here. So let me delete this ones. So we have academic outcomes, and then behavioral engagement. This is the performance score, and then this is the total effect. So we can report on these two tables about the effect. So the effect of behavioral engagement and then academic outcomes is given about 39.1%. And then how well the data assess predict outcome is the next. Okay, so it is being ranked second here. But its performance, let's look at that. The performance is what was the worst here. So the diagram will help us to explain this further. Let's go to the important performance map. So from here, we can see that skills development is the one with the highest effect, and then also with the highest performance, which are close to 60. Okay, so if you have to plot that, you can even work on this diagram here. When you click on the properties, you can show text map and all of that. So let's see what happens. You can also relabel them the way you want it to be. So, and then what else can we do? You can also change the skills. So the minimum values for the X here start from negative 0.00 something, and then the highest is about 0.43. So you can also change it to maybe 5, and then it also recalculates for you. You can change it to 10. Okay, so 10, it will make our list visible. Let's see 6. Okay, so 6 is okay. Or let's say 5 is visible. And then the minimum starts from 1, so we can also 0.1. So we can turn this one 0.1 so that we can have it very clearly. You can also show the horizontal lines, vertical lines. Okay, vertical 0 line and then horizontal 0 line, which appears here. So, and then rotation. And then let's look at the y-axis. Show minor clicks. And then rotation. Okay, let me restore the photo and see how that changes. So I think this one depends on you, how you want your diagram to be. All right. So that one is up to you. This is the vertical 0 line. Okay, so now this is showing the horizontal 0 line and then the vertical 0 line. I don't know if you can see it, but it appears slightly down there. So that is it. So this can also help you to give further recommendations about how, management or probably policymakers should, if they have to do some infrastructure or whatever. So here we can see that skill development has the highest importance. It has the highest effects. And then it's also giving us very good performance score. So the performance is good. And then, because if I have to trace this one here, there's 60. So this is giving us the highest performance. And then its effect is also giving us the highest. So it means that we can make decisions and say that, oh, platform quality is giving us a very low effect here. And then it's not really important based on how the questions are being answered. It means that probably there's an issue with the quality of the platform, or they don't really pay much attention to the platform quality. And for that matter, maybe if management wants to make decisions, they want to improve on platform quality so that the students will have access to more quality platforms or engagement within the platform. So as to how you want to interpret it depends on you. And this is that of the indicators. Okay, so the various indicators have also been plotted here. And you can also work on the properties as well. So I think so far so good. Is there any question? We can end our class here with performance analysis. Any questions so far?